Victor Kai is an 11th grader from Parkland High School in Allentown, Pennsylvania, United States. He aspires to be a future researcher in electrical and computer engineering. He has been an enthusiastic participant in many science fairs with projects ranging from Arduino-controlled systems to SDR-based RF systems. He has won many awards in state and national level science fairs, as well as in math and physics Olympiad competitions at the middle school and high school level. However, today is the first time he will share his project in a professional forum. He is very excited about this amazing opportunity. Please welcome Victor Kai.
Hello, I am Victor Kai. I'm a high schooler at Parkland High School in Allentown, PA, and my presentation here is on designing a narrowband radar using GNU Radio and SDR for tomography and indoor sensing. The goal of this project was to design a low-power narrowband radar using software-defined radio, or SDR, for tomography and indoor sensing. To achieve a 15 centimeter resolution, a traditional radar would require 1 gigahertz of bandwidth and a lot of power, which makes it a poor candidate for amateur research. Meanwhile, a regular SDR unit can give 4 megahertz in bandwidth, which makes its theoretical resolution over 37 meters, which isn't very useful for short-range applications. That's why you can find many SDR Doppler radars with motion sensing capabilities, but no SDR-based distance sensing radars. This project was able to create such a SDR distance sensing radar with 15 centimeter range resolution using only 4 kilohertz of bandwidth, and I did this by combining the low power SDR with the lesser known radar algorithm called multiple frequency continuous wave, or MFCW, which uses phase differences in multiple frequencies to calculate the distance. Here's my homemade system. It includes 2 SDR units with 1 per frequency, which use the antennas inside of these coffee cans as transmitters to transmit toward the radar target. The target reflects the signals back to the receiver antennas on top, which allows the SDR to measure the phase difference and thus calculate the distance. The target is mounted on a ruled camera slider for comparison with the calculated distance, and I wrote the software with GNU Radio with graphics for demonstration. First, some background info. A traditional distance sensing pulse or MFCW radar requires a lot of bandwidth, and this is not feasible for an SDR implementation. In fact, in order to get 15 centimeter resolution, it requires about 1 gigahertz of bandwidth. This is because they rely on an ultra-wide bandwidth to create a very short pulse width to increase the distance sensing accuracy. However, this increases power consumption as well as interferes with other wireless devices. My proposed narrowband solution uses MFCW, which stands for multiple frequency continuous wave, and this uses 2 continuous waves at 2 different frequencies simultaneously in order to calculate the distance using the phase differences. For example, as shown in this diagram, we have a 2.5 gigahertz and a 2.4 gigahertz signal, 2 different frequencies, and these give 2 different wavelengths. That means that once they bounce off of the target, they will come back with different phase differences, and in fact the phase difference between these 2 frequencies will increase linearly, so you can use the phase differences to calculate the distance. My goal is to design an MFCW radar that can be made with a low cost and low power 2 megahertz bandwidth SDR unit and can still achieve the superior 15 centimeter accuracy of the expensive traditional radars which use the 1000 megahertz ultra wide bandwidth. And this proof of concept opens the doors to many short-ranged radar applications with low power and low cost SDR technology, including autonomous vehicles, smart homes, medical sensing, imaging, and tomography. So my first MFCW radar design used a single SDR, and the idea is in order to get onto multiple frequency channels for my MFCW, I would hop between the frequencies I needed with a single SDR. So this slide shows the mathematics behind that. First, we take one of our, say, two signals. Say we take the 2.5 gigahertz carrier, and we modulate a 2 kilohertz signal on top of that to give us a transmission signal. And then I can send that signal, and it gets reflected back from the wall and received. And that comes back with the phase information, which is shown in red. And we want to recover that information because that's what we can use to measure the actual distance. So in order to do that, we multiply by the conjugate of the 2.5 gigahertz carrier, which recovers the 2 kilohertz signal with the phase information attached. And then we can multiply by the conjugate of the original 2 kilohertz signal to give us just the phase information that we need. Then we can do all this again with our second frequency at 2.4 gigahertz in order to give us two phases, and then we can subtract those to calculate the distance using the phase differences. This is the design for my single SDR system. We have two tin cans as antennas. One's transmit and one's receive, and I connected both of them to a single SDR unit. And then we have the camera slider rail and the target. And then the antennas are optimized for the range in use around the 2.4 to 2.5 gigahertz range. This is the actual code for my single SDR design in GNU Radio. It starts with a 2 kilohertz signal source, which is then modulated. This mostly reflects the mathematics that I showed earlier. It's modulated and transmitted and then received over here in this block, and then sent to calculate the phase by multiplying the conjugates, and then we can display the calculations through GNU Radio as well. Additionally, at the top here we have the switch, which allows us to switch between our 2.4 and 2.5 gigahertz carrier rates. Here are my results for my first design. I was able to successfully recover the 2 kilohertz signal even after being reflected. I also detected the correct phase across the distance that I tested it at. However, the major issue was that my frequency hopping idea did not work, and this was because my specific SDR, the Lime SDR Mini, whenever it switched frequencies, the starting phase would be random, or at least not predictable. So that messes up my calibration. So unfortunately, I couldn't pursue this design further until I find a better SDR. But until then, I have to come up with a different solution. So this solution would come in my second design, which is a dual SDR design. I have two SDRs, one on each of the two frequency channels. That way neither SDR has to switch. And also, in order to minimize the increase in size, instead of adding two more CAN antennas, I added two compact Wi-Fi antennas, and then now the CAN antennas are the transmitters, and the Wi-Fi antennas will be the receivers. And then in order to separate all the antennas from each other to try and avoid coupling, I 3D printed a mounting bridge to keep the antennas further away from each other. So here is the GNU Radio code for my dual SDR design. It includes a channel A and a channel B. which are essentially just slightly edited from the previous single SDR version and then duplicated. And then there's a portion which combines the two and then calculates the distance. And then this allows me to have when I run this, I get the GUI interface, which allows me to visualize the two waveforms and their phases, as well as display the phase delta and the calculated distance. So the quickest way to test my design was to put the target at integer multiples of one of the wavelengths. That way, one of these sine waves would give 0, while the other one would give another number, which can be used to calculate the distance. So I put the target at integer multiples of the wavelength, or at least incremented it so that the round trip distance increases by a wavelength each time. And below we have the data, which is very good. The actual data and the calculated distance match up very well and are within 5 centimeters of the actual, which is well within my 15 centimeter expected. However, when testing for arbitrary distance calculations, I found an interesting problem where every so often in a certain region, it would always give me a negative distance. And so I developed a simulation to try and figure out why this was occurring. And you see the simulation here, which includes some screenshots from an Excel sheet. The first graph is a plot of the two phases for the two different frequencies, and basically I would subtract one phase from the second one in order to calculate the distance. However, we see that in the regions where the orange graph drops from pi to negative pi, the blue graph has a short period where it hasn't dropped yet. And in that period, actually, when I subtract the orange one from the blue one's phase, we get a negative number, which causes those negative distance calculations. So the solution is to detect that and then add 2 pi to the phase whenever that happens. And that is my algorithm for fixing the arbitrary distance calculations. So now here are my testing results for arbitrary distance calculation again, but this time with my algorithm to correct erroneous results. I was successful in being able to correct the erroneous results, which are shown as the red dots in the top graph. Additionally, I successfully have a 15 centimeter accuracy within my 70 centimeter range, which matches the accuracy of those traditional radars with much less power and much less bandwidth. However, my distance calculations have a slight periodic oscillation where they should be nice and linear, with degrading accuracy as the distance increases. And I'm not entirely able to explain it yet. One possibility would be a nonlinearity in the signal phase. As you can see, the signal phases should be a nice sharp sawtooth. However, instead they show a little bit of a curve in the tooth part. This is likely a result of a nonlinear amplifier phase, and ideally we want them to be nice and linear so that our data for the arbitrary target distance looks more like the data that we had for the integer multiples of the wavelength. So here's how I conduct my experiments. First, I set the target to the 30 centimeter mark. This is used as a zeroing distance, so that this distance is considered 0 and everything is measured from there onward. In order to set it as 0, I need to line up the phases for the transmit and receive in both the 2.5 gig and 2.4 gig signals, and I do that with a phase shift here, which allows me to line them up. So now they're both zeroed out, and the distance shows 0. So now, in order to make a graph like on my board here, with arbitrary target distances, I push back the target by 1 centimeter, and then I record the distance that it shows on the screen. And I do that all the way backward, 1 centimeter, 2 centimeters, 3 centimeters, and so on, in order to create a graph like that. And then for testing its use for tomography, I can set up a piece of drywall in front of all 4 antennas here, which blocks all 4 of them, but the radar is able to sense through the wall and see my hand moving behind the wall. So tomography, specifically the ability to see through walls, is very useful in various situations. For example, law enforcement officers can use it to avoid walking into an ambush, which minimizes casualties. Additionally, emergency responders can use it to see through collapsed buildings to locate survivors. And it also has many medical uses for penetrating through the human body. Now, in order to test these, I set up drywalls, wood, water, and oil in front of all 4 antennas in order to create a barrier. However, the radar was still able to sense through the wall or other barrier, which makes it a good candidate for both security and medical tomography. Additionally, there are several types of motion that it can detect. For example, we see that if it's just background noise, then it shows a single distance measurement for just a background. And then for a slow moving target, you can see the histogram slowly moving towards or away from the target. And then for a fast moving target, there's a more unstable waveform and a more fluctuating value. So it can detect all these types of motion with the help of the histogram, which is a good illustration of that motion. In conclusion, my project was able to demonstrate a new approach in making the narrowband radar more accurate and low cost by combining the unpopular MFCW radar algorithm and the low-cost SDR, which can lead to many short-range radar applications. This MFCW SDR-based distance sensing radar is made with a range resolution of 15 centimeters while only using a few kilohertz of bandwidth. A self-made distance sensing algorithm was also created with the capability to correct erroneous results from direct delta phase calculations. And for comparison, a traditional radar would have to use 1 gigahertz of bandwidth to achieve the same 15 centimeter resolution, which means I was able to achieve the same resolution with more than 5 times magnitudes less bandwidth. As for future research, I'll be focusing on 2 points, trying to get the starting phase to be more stable when switching frequencies. That way I can use a single SDR design, which also cuts even more cost, and then improving the accuracy by possibly compensating for any systematic error in nonlinearity, or otherwise making the nonlinear phases more linear. Finally, I would like to thank the GRCon committee and reviewers for giving me this opportunity to present and publish, and thank you to the GNU Radio's wonderful community spirit in providing free and intuitive tools to enable young enthusiasts like me to start research at the high school level. And to all the professionals at GRCon, If you have suggestions to help me with my amateur research project or need a volunteer like me for your research, I would greatly appreciate it. Thank you for your attention.